Hello everyone, I am Antonio. I am in my third year of PhD, and today I'm doing this presentation for these doctoral meetings. I will start talking about the motivation, what I did in the first year, covering some results I already presented briefly, but for those who were not here and don't know what I'm doing. And then I will update the status of my thesis from the point I presented last year with any relevant information we included in this last year, and finally, I will mention some important achievements of this thesis. I will start with some motivation. There are many examples in the aerospace field where turbulent flows are present and may affect the performance of a certain device. And this is why we want to study turbulence to understand it better and hopefully to learn how to deal with it and how to control it. And here I bring some examples like a classical case of an airfoil or a wing around which a turbulent boundary layer can be developed. We can have effects like transition to turbulence related to drag, and this is an effect that we would like to control. We also have, for example, mixing, which is an effect happening inside combustion chambers and affects the efficiency of the combustion process. We also have the aircraft jet, which is also related to drag, or we have the swirling jet animation showing how fuel is injected inside the combustion chamber, just as other example with a clear impact on efficiency. We can modify the flow with something as simple as a change in the geometry, but to apply properly control strategies to adapt it to different environments, to different operating conditions, we can consider passive control or active control strategies, which is where we are aiming. Of course, this implies more complex systems with sensors to monitor continuously some part of the state. We need to compute the actuation. We have to actuate the system somehow to produce a change, and all this implies some power consumption and is obviously more complex to develop. And well, this thesis focuses on the sensing part needed for a closed loop flow control application. And we want sensors to provide us information about the state of turbulence in the vicinity of the wall of our device to be used to compute the actuation we need. But we cannot use devices such as the traditional hot wire probes because those are intrusive measurement devices, and these may disturb the flow, producing some further turbulence, which is an effect that we want to avoid. So we want to take measurements at the wall with non-intrusive techniques. We cannot measure the velocity field right in the wall, but we can measure other quantities that could be related to turbulent structures such as we have pressure, we have wall shear stress or heat transfer that could be related, and this is an additional step to implement to have the estimation of the turbulent flow field from these wall measurements. Here we have some examples from the literature that can be considered as the baseline for this work. For example, wall measurements have been used in these references to estimate the velocity field in wall parallel planes, and the objective of this thesis is to do this same thing but in 3D, using as baseline these neural networks used previously in 2 dimensions. Furthermore, as some possible application of this methodology for control purposes given the sensing system, we can find several suitable applications based on artificial intelligence for this control algorithm. During the first year, I did some literature review about different topics concerning this thesis, like control system, reinforcement learning, and genetic programming for turbulent flow control. And I learned about neural networks, about deep learning, and I also got familiar with different experimental techniques to be used in the experimental part of this thesis and the facilities we have in the lab. And I also designed this neural network for and for this flow estimation task that I already discussed here last year. In year two, I closed this work of flow estimation, including a physical interpretation analyzing not only the performance of the neural network. We included also a physical interpretation, considering what types of turbulent structures we have in the original fields and in the reconstructed field, considering what the neural network can recover. And I also did an experiment with swirling jets without control, which was useful to start developing an experimental setup for sensing purposes in a possible real application configuration. And then in year two and year three, I started proposing some alternatives to the methodology we presented with the 3D GAN, basically trying to challenge somehow the methodology to do the same thing, to estimate the same thing using less sensors and less information as input. Here we have some cases with where, well, we have analyzed the effect in the resolution of sensor, the effect of the sensor that we are using, just using one of them instead of the three of them. We have assessed the effect of the sensor arrangement. We have also assessed the effect of noise in measurements, and here we have some results where we can see how the mean square error can increase where we use less sensors, but the increment in the error is not proportional to the important reduction in the number of sensors that we may have in the different cases. And at the moment, I am developing an experimental campaign with a channel facility where we are using infrared thermography and PIV for the velocity field estimation. And the idea is to make a validation of the 3D GAN methodology in an experimental setup, because this methodology was previously developed and presented based on data from a DNS. And I am doing this as part of the research stay in Politecnico de Torino at the moment. And to conclude, I would like to mention some achievements. Those are the conference where I have participated, those from the first year. I presented there the methodology of the neural network. Then in the second year, I presented in the first one the experiment of the swirling jets, and in the other two, the complete work of the 3D GAN with the physical analysis. And then in the third year, I already presented in the first one of these the alternative cases I just show you where we are challenging the 3D GAN. And in this second conference of this year, I expect to present in at the end of the summer the results from the experimental campaign I'm doing right now. Regarding journal articles, there is one we submitted last year which is already accepted for publication, and there is a second work which we submitted and is at the moment in process of review. Also, I would like to mention the research stay on which I am right now, and it is a very nice opportunity that came to me, and I expect to get very important achievements from it for my thesis. And also, I would like to mention these courses I enrolled, four of them regarding very topics very focused on my thesis. Those are technical seminars, and I also did these two courses from the doctoral school for more generic topics, but I consider those interesting for my thesis. And those are the projects funding my thesis. I'm covered by the FPU program, and other expenses like conferences are being covered by the European Research Council with this Nextflow project. And that's all from my side. Thank you for your attention.